In the previous video, we learned how to solve a single linear congruence modulo n, but now we're going to address two of them. So we did learn how to solve a single linear congruence. Ax equivalent to b mod n has solutions if and only if the GCD of a and n is a factor of b, and then you can find it, etc., etc. What if I have, however, multiple equivalences in the same variable, like this? Now, I want a1 times x to be equivalent to b1 mod n1. I want a2 times x to be equivalent to b2 mod n2, and so forth all the way until akx equivalent to bk mod nk. The coefficients ai might be changing from line to line. The desired outcomes bi might be changing from line to line. The base ni might be changing. But x is not. It's the same x in every line here. So we're trying to find integers that solve all of these linear congruences at the same time. It might not always be possible. For example, letting just two linear congruences be on the board. A1 is 1, B1 is 0, N1 is 2. A2 is also 1, and N2 is also 2, but now we've changed B2 to be equal to 1. So we want 1x to be equivalent to 0 mod N2, and we want 1x to be equivalent to 1 mod 2. These can't be true at the same time, because both of these amount to saying, is x equivalent to 0, but also equivalent to 1 modulo 2? And nothing will be equivalent to both 0 and 1 modulo 2. Sometimes, however, we can solve them. For example, if I wanted 1 times x to be equivalent to 1 mod 2, and I wanted 1 times x to be equivalent to 1 mod 3, we observe that x equals 1 definitely solves this. I get x equals 1 on both of them. But negative 11 is a non-trivial solution to both of them. 1 times negative 11 is in fact equivalent to 1 mod 2, but also equivalent to 1 mod 3. Now, before tackling this very general problem of lots and lots of linear equivalences, let's just suppose we have two of them. So we want a1x to be equivalent to b1 mod n1, and we also want a2x to be equivalent to b2 mod n2, and that's it. Are there any x's that solve both at the same time? Before trying to solve many equivalences, let's see if we can at least figure out how to deal with just two of them. Well, any x would have to solve each equivalence individually, right? If one of these equivalences has no solutions at all, then I'm certainly not going to find something that solves both of them. So let's go ahead and assume that each equivalence has solutions on its own. In other words, the GCD of A1 and N1 is a factor of B1, and the GCD of A2 and N2 is a factor of B2. We also know that any single equivalence will be solved by x being equivalent to something modulo n prime, where this new base is the old base divided by that GCD, and b prime is just the product of A inverse with the original b. So if solutions exist, that means the GCD of the coefficient and the base is a factor of the target value, in which case you would cancel it out from everything and get a times x equivalent to b mod n prime, where that was just dividing out by this GCD, and then whatever value is left over multiplying x, it's now relatively prime to the new base, so it has an inverse, so multiply by it. So if one equivalence has a solution, it will end up looking like this: x equivalent to something mod something else. So each of the individual congruences would eventually be solved to have that kind of form. So what we're going to do is assume that we've already done that work. Okay? In other words, our general problem of two equivalences with one variable is just going to look like this. We've already done the work of accounting for those coefficients and seeing if solutions even exist. And both of them have now been reduced to x is equivalent to something mod n1 and something mod n2. These would presumably be different b's and different n's from this problem up here, but each line, if it has solutions, can eventually be modified to look basically like this, and we're just assuming we've already done that. To give a nice standard format for our problem, the coefficients on this side are just 1. So now we have a general system of two equivalences in one variable. We want a single x that is equivalent to b1 mod n1, but also equivalent to b2 mod n2. Are there any such x's? Well, here's our first theorem. If the two bases are relatively prime, then there is in fact one solution modulo the product n1, n2. Assuming the two bases are relatively prime, two different but similar looking results follow. I'm going to pick something which is n2 inverse mod n1. Because these two numbers are relatively prime, n2 has an inverse mod n1. But n1 also has an inverse mod n2. So y1 is n2 inverse mod n1. I'm making the subscript of the base match the subscript on my y. So y2 is n1 inverse mod n2. Now let's look at y1 times n2. If I'm working modulo n1, y1 was exactly the inverse of n2, mod n1. So modulo n1, the product of these two things is equivalent to 1. However, if I take the same number, y1 times n2, but I don't look modulo n1, I look modulo n2, this is a multiple of n2, which means it's equivalent to 0. So this is a number that is equivalent to 1 mod n1 and 0 mod n2. So therefore, if I multiply this by b1, b1 y1 n2 is just this multiplied by b1, so it's equivalent to b1 mod n1, or this multiplied by b1, so it's still 0 mod n2. So now we've constructed one number that is equivalent to b1 mod n1 and equivalent to 0 mod n2. Similarly, if I just start playing around with indices, instead of doing y1 times n2, I do y2 times n1. This is a multiple of n1, it's equivalent to 0 mod n1, and I can multiply by b2 and still have that. Since y2 is n1 inverse mod n2, y2 n1 is equivalent to 1 mod n2, and if I multiply that by b sub 2, we get b2 y2 n1, equivalent to b2 mod n2. It's the same work as before, I'm just sort of playing around with my indices and getting it slightly different looking. So I have one number equivalent to b1 mod n1, good, we wanted that, unfortunately equivalent to 0 mod n2. I have another number equivalent to b2 mod n2, good, but equivalent to 0 mod n1. Now I just have to add them together. Because mod n1, the first number was equivalent to b1 and the second was equivalent to 0, but mod n2, the first is equivalent to 0 and the second is equivalent to b2. So we have managed to simply construct by hand a number x that solves both of our desired equivalences. Now let's suppose there's another solution. So this x happens to be one solution, and I happen to have another one. Well, if x is equivalent to b1 mod n1, but so is x prime, then their difference is equivalent to 0 mod n1. But if x is equivalent to b2 mod n2 and so is x prime, then their difference is equivalent to 0 mod n2. Being equivalent to 0 modulo something is the same as having that base as a factor. So n1 is a factor of this difference, but so is n2. However, these two numbers are relatively prime. That was back in our assumptions at the beginning. So if these two numbers are factors of the same thing and they were relatively prime, then their product is a factor of that number. Well, if n1, n2 is a factor of this difference, then those two solutions, the one we constructed by hand x and some other solution I supposed I had, must be equivalent mod n1, n2. So assuming n1 and n2 were relatively prime, we were able to find a solution, and we were able to find that any two solutions must be equivalent modulo n1, n2. So mod n1, n2, there is a unique solution. Let's work through an example of this technique. If the two bases are relatively prime, we didn't just derive that solutions exist, we actually found exactly what to do to find them. Find inverses of one base modulo the other and exploit those numbers. So let's find all solutions to the equivalence. X is equivalent to 3 mod 7, but it's also equivalent to 5 mod 11. The two bases are relatively prime, so we can use the technique from the previous slide. We need to compute the inverses of one base modulo the other one. We can compute that 7 inverse is equivalent to 8 mod 11, 7 times 8 is equivalent to 1 mod 11, but 11 inverse is equivalent to 2 mod 7. 11 times 2 is equivalent to 1 mod 7. So we simply let x be the desired target mod the first base times the inverse of the second base mod the first base times the second base, plus the target modulo the second base times the inverse of the first mod the second times the first base. You could just copy this down from the previous slide or find it in the textbook. This works out to be 3 times 2 times 11 is 66, 5 times 8 times 7 is 280, so 66 times 280 is 346. But let's just look at it written as this. When taken mod 7, this term vanishes. So modulo 7, I can ignore this term here and only focus on this one, in which case 2 times 11 is going to be equivalent to 1, and I just get out the 3, which is what I wanted mod 7. If I work mod 11, the first term vanishes. 8 times 7 is equivalent to 1, leaving behind just the 5 as desired mod 11. Okay, so this does work out to be x equivalent to 346 mod 77. You could simplify this if you wanted to, but we weren't asked to find the smallest solutions or anything like that, so we found all solutions. It's all integers equivalent to 346 modulo 77. So why do the extra work if you don't have to? Students frequently assume they're supposed to reduce this down. We weren't asked to. Why risk making a mistake? Let's keep working more examples. For example, let's find the smallest positive solution to the following pair of congruences. Well, our bases 40 and 21 are relatively prime, so we can use the same technique. We have to find the inverse of 40 mod 21 and the inverse of 21 mod 40. Now 40 is equivalent to 19 mod 21, so instead of 40 inverse, we can find 19 inverse. Phi of 21 is 12, so by Euler's theorem, we actually get that 19 to the 12th is equivalent to 1 mod 21, which means 19 times 19 to the 11th is equivalent to 1 mod 21. So this number right here is equivalent to 19 inverse mod 21. So we could compute 19 to the 11th mod 21. What will be easier, in fact, however, is to rely on the fact that 40 is 2 cubed times 5. So instead, let's find 2 cubed times 5 to the 11th mod 21. Why is this actually a little bit easier? Exponents distribute, so 2 to the 3rd to the 11th would just be 2 to the 33rd. 33 is 12 plus 12 plus 9. But since 2 is relatively prime to 21, 2 to the 12th is also equivalent to 1 mod 21. So both of these terms are just 1s, leaving behind just 2 to the 9th. We can just compute that out by hand. 2, 4, 8, 16, 32 would be the next power of 2, but mod 21, that's equivalent to 11. How do I keep generating powers of 2? I just keep multiplying by 2. 2 times 11 is 22, but that's equivalent to 1 mod 21. And then I would just start going through the same pattern. And now let's just count. 2 to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th. 2 to the 9th is 8. So 2 to the 9th is the same thing as 2 to the 33rd mod 21. So 2 to the 33rd is equivalent to 8 mod 21. 5 to the 11th, I could go through a similar sort of looking for patterns business, but 5 mod 21 is equivalent to negative 16. Why is this nice? Well, negative 1 to the 11th is just going to be a minus 1, but 16 is 2 to the 4th. So 2 to the 4th to the 11th is 2 to the 44th. I'm going to make that 2 to the 12 plus 12 plus 12 plus 8. Each of these is the same thing as 2 to the 1st, and 2 to the 8th we worked out to be equal to 4. So overall, 5 to the 11th, same thing as negative 16 to the 11th, is the same thing as negative 4 modulo 21. So ultimately, 8 to the 11th is just 8, 5 to the 11th is just negative 4. Therefore, 40 to the 11th will be the same thing as 40 inverse, is negative 4 times 8, negative 32, same thing as positive 10 modulo 21. Similarly, 21 inverse is actually just 21 mod 40. 21 squared is going to be equivalent to 1 modulo 40. So having computed both of these inverses, we go through the same business. Target value mod first base, inverse of second base mod first base, times second base, target value mod second base, inverse of first base mod second base, first base. All of this works out to be 11,938 mod 840. But in this problem, we were asked to find the smallest positive solution. So I'm just going to apply the division algorithm and find the remainder when 11,938 is divided by 840, and it turns out to be 178. So the smallest positive solution is 178. Let's make some remarks about the procedure we've developed here. If the two bases are not relatively prime, you do not get to conclude there are no solutions. We have a technique for finding solutions if the bases are relatively prime. It involves finding the inverse of one base modulo the other, so you need them to be relatively prime. But if they aren't relatively prime, it doesn't mean no solutions exist, it just means that technique won't work. For example, if I want x to be equivalent to 1 mod 10 and to 6 mod 25, 31 is a solution, even though the two bases are not relatively prime. So it's possible to have a non-trivial appearing system of equivalences whose bases are not relatively prime and solutions do still exist. So we're going to need to develop something else to try to solve when does a system have solutions if the bases are not relatively prime to one another. What should be clear to you, however, just from the examples we've done, is that to solve these equivalences, you need to compute modular inverses a lot. You need to do it fast, and you need to do it with very few mistakes. Now, if you have a computer handy and you know how to use it to generate modular inverses, that's great. If these are relatively small numbers, 3 digits or smaller, then you might be expected in an exam environment to do it by hand or just with a simple calculator, so practice and make sure this is something that you can do. Find modular inverses quickly.